So let's look at pendulums. Pendulums are any sort of system that has a mass, some sort of mass hanging on the end of a cord. There's a couple assumptions we make about pendulums, and the first of which is that the cord itself, it doesn't stretch. It shouldn't stretch. Any idea why that might be? Why is it important that the cords of these pendulum don't stretch? Would that lead to really consistent repetitive motion? Right, no, it wouldn't. If we were going to, if we had a cord that was stretchy, that might lead to really inconsistent back and forth type motion. And the whole point of it being simple harmonic motion is that it's identical and repetitive. So it doesn't stretch, and we assume that the mass of the cord, you might want to even put that in there, not just the mass of the cord is negligible. And so all that means is that we have to have a relationship between the cord and the mass on the end. That's a high ratio toward this mass, right? We just want the cord and gravity really to not affect the mass of that cord. Does that kind of make sense? We just want the mass on the end of the cord to be the one that's really kind of dictating the motion and where it goes. So if the cord itself weighs too much, it will affect that back and forth motion of the pendulum. Okay. So that's basic pendulums. We see pendulums a lot like in big old clocks. That's a really common place that we see pendulums. They swing back and forth. We see them, let's see where else. Even household things like a swing set. You know, if you're on a swing and you're going back and forth, that's considered a pendulum. Any sort of back and forth motion. Okay, so let's look at this pretty easy problem here. It says a pendulum is observed to complete 23 oscillations in 58 seconds. Determine the period and frequency of the pendulum. And so I even gave you clues as to what each of those represent, right? Period and frequency. And these are just really simple math problems that go into that, okay? So if we have 23 oscillations per second, 23 oscillations for 58 seconds, that would be solving for frequency, right? To solve for frequency, we would take 23 oscillations over 58 seconds. And that gives us, I don't know, go ahead and run it all the way out. I don't like fractions, so I like it in decimal. 23 divided by 58 gives us 0.396. And you can use that unit as oscillations per second, or you could label it as hertz. That's the same thing. Okay, Hz is another unit for frequency, and it just means oscillations per second or cycles per second or whatever you want to call that. Okay, and then to find period, you could do T equals 1 over F, and you could solve for it that way, or you could just turn it around and say 58 seconds per 23 oscillations. Either way, that's going to get you the same value. So that's 2.52 seconds. And then you might even see it per oscillation, but usually we just leave it as just seconds because we know it's over one oscillation. So either way is fine, but period would be 2.52, frequency would be 0.396 oscillations per second. So in these equations for period and frequency of a pendulum, the thing that's different and the things that tells us it's for a pendulum is that L variable. What do you think L stands for? Exactly, the length of the cord. Okay, L stands for length of the cord, and G obviously stands for the acceleration due to gravity. If we are on Earth, then that value is 9.8. If we're not on Earth, then that value might be something else. Okay. The reason we take gravity into account for these problems is because gravity is what is pulling that mass back into its equilibrium point, right? It's conservation of energy and its gravity. So we're keeping that hanging and not moving in a full circular path. Okay. Down here it says, as long as the cord can be considered massless and the amplitude is small. And so all that means when we have amplitude of a pendulum, here's my pendulum. The amplitude is the degree to which the pendulum is pulled upward. Okay, so this angle right here would be considered the amplitude. How far out from center are we pulling that pendulum? That's the amplitude. And so when we say small, we usually try to keep amplitude, in the 30-degree mark from center, right? We're not going to get up to pulling it up to 70 or 80 degrees from center because that will lead to some gravitational effects that pull it out of its nice circular path. Okay, so amplitude has to be relatively small for pendulums to stay really consistent. Okay, and so that means we wouldn't try to pull our pendulum, way up here or way up here to get it started. We want to keep that amplitude relatively small right there. Okay, questions with that? All right, let's go ahead and try one here. This says a pendulum has a 0.54 kilogram mass and the cord is 1.4 meters long. What frequency does it have? Did you see in our equation anywhere that mass gets put into our equation? No. So the mass on the end of it really doesn't make a difference for us. Okay? If I'm going to solve for frequency, I'm going to take 1 over 2 pi square root of G over L. At least I think I did. Yeah, okay. So frequency equals 1 over 2 pi times square root of 9.8 over 1.4. And then I'm just going to work from the inside out with that equation. So I'll go ahead and do the inside of the radical first. 9.8 divided by 1.4. I'll take the square root of that. And then you have to multiply it by 1 over 2 pi. Or if it's me, I'm just going to divide by 2 pi, right? I'm going to go divide by 2, divide by pi. Or divide by parentheses 2 pi, or however you want to do it. But I here get a frequency of 0.421 hertz. Okay, so run that through. Make sure you're getting the same thing in your calculator. More commonly, we'll solve for the period because that tells us the time. Frequency is kind of it's kind of a moot something to solve for because you'd really rather know how long it takes rather than how many cycles it makes in a second, right? That doesn't really make much difference to us. So more often, we'll solve for period. So this one says the pendulum has a period of 0.98 seconds. What is the length of the cord? So this one is the algebra will be a little different because you're solving for L, which is inside of that radical. T equals 2 pi times square root of L over G. So we know T equals 0.98 2 pi square root of L over 9.8. Okay, so are we good with the algebra through this? I'm going to move 2 pi over. I think we're probably good with this right now, but and that gives me 0.156 equals square root of L over 9.8. And so then I'll square both sides. And then I'll take that times 9.8. And I get a cord length equal to 0.238 meters. Okay, we do want the length of our cord always to be in meters because if our acceleration due to gravity is meters per second squared, we have to make sure those units cancel out. Okay?